Okay, so we're going to finish lesson 6.1 today, but today we're going to look at strictly exponential decay functions. We looked at growth yesterday, and today we're going to look at what the decay function looks like. There are going to be some similarities, but there are also going to be some big differences. So, first of all, let's start with a big difference. If you notice, the B number, you might think, well, that's the same function that we looked at yesterday when it was exponential growth. And you're partially right. It does look the same in format, but the huge difference is this B number, the number that sits directly underneath the exponent. Yesterday, when it was growth, B was greater than 1. For decay, B will always be described as a number that sits between 0 and 1. So it's going to be a fraction or a decimal, some value that is between 0 and 1. And if you recognize that, you know you've got the graph of exponential decay. So here's some more similarities. Just like yesterday, this is going to be a continuous graph, just like growth. Here's a difference. Growth, from left to right, we said increased. Decay, you'll see in just a moment, is a decreasing graph. And just like growth, decay is also a one-to-one. So before we get into domain range and the asymptote, let's just put an example up, just like we did in the previous lesson. We'll do a simple example here. I'll do y, or we could have used f of x. It really doesn't matter. But let's do y equals 1/2 raised to the x power, just to get an idea of what decay looks like. You notice b is between 0 and 1, so this is classic decay. We're going to make our table for the parent. And once again, if I input 0 for x, 1/2 to the 0 power is 1. If I input 1, then the output is 1/2. So just the opposite of what happened yesterday. Yesterday, as I chose bigger numbers for x, I got bigger numbers for y, and they got big in a hurry. Today, as I choose bigger numbers for x, I'm going to get smaller, closer to the x axis values for y. When I go the other direction, if I raise 1/2 to the -1, that's 2. You just flip over the base and then change the exponent to positive. If I raise 1/2 to the -2, I get 4. 1/2 to the -2 is the same thing as +2 to the +2 power. So let's plot these points. We still have 1 as our y-intercept, just like yesterday. 1/1/2 would be here. And then 2 1/4, a little closer to the x-axis. Then we can plot -1 2. You can see how we're getting further away. -2 4. And we connect those dots with a curve. And this is a perfect example of what exponential decay looks like. We're approaching the x-axis this time from the other direction. We're approaching the positive x-axis instead of the negative x-axis. The domain's still the same as growth, all real numbers, using interval notation. The range, the same as growth, at least for the parent. The range is going to be all y values greater than 0. So using interval notation, we could say this, from 0 to infinity. Remember, 0 is not included, and that leads us to this term asymptote again. Can somebody give me from yesterday's lesson what the definition of an asymptote line is? Yes? Dalton? Okay, I think I know what you mean, but somebody want to clarify a little bit? It's a line that...
a graph approaches but doesn't.
Okay, so it's a line that our graph will approach but never touch, and that's the same for decay as it was for growth. It's just approaching from a different direction. So the asymptote is once again going to be y equals 0. Okay, so with that said, we know what the parent looks like. Let's do one more little example here, just for good measure. Here is a parent, no translation, no dilation. So let's make our table. And when these are just graphs and they're not word problems, we can use these same inputs every time. If I input 0 for x, I get 1. If I input 1 for x, I get output 1/3. Input 2, I get output 1/9. If I go to the negatives of these, which you always should, if I input -1, I get output 3. If I input -2, 1/3 to the -2 is the same thing as 3 to the +2, which is 9. Plot those points. Here's my y-intercept. 1/3, getting a little closer. -1, 3. -2, 9. And connect those dots. And we have our decay graph. Approaching but never touching. And then we're taking off pretty quickly as the values for x get more and more negative. Any questions so far? And the last thing then we need to do is state the domain range. So domain is all real numbers, so we'll state it like this. Range, all values for y that are greater than 0. From 0 to positive infinity. Any questions so far? All right, so let's take a look at some transformations. And the good news here is the transformations for growth work just like they do for decay. So there's really no change in the way we come up with the transformed parent function. Okay, so let's start with the parent. It's important that you can pull the parent out of this, and the parent function that's being transformed is f of x is equal to 1/4, that's the b, raised to the x power. So let's make a table for the parent. So I'll just call on some of you, John, for input 0 into the parent. I get 1. 1/4 to the 0 is 1. Sam, input 1, output 1/4. Dalton, input 2, I get output, just square both of these, 1/16. Okay, Riley, input -1. Four. And Kennedy, input -2, 16. Any questions so far? That's the parent. And now it's important to me that you understand how these numbers, there's actually 3 of them, impact the parent. This is where transformations and understanding transformations comes into play. So we're just going to break this down. We're going to slow it down a little bit, and we're going to do one step at a time. So my next table will take care of this 2, this a number in my function. And what that tells me, it's a dilation. It's actually called vertical stretch. And the way I accomplish vertical stretch is I take 2 and I multiply it times each of the y's of the parent. So I'm just going to call this table times 2 because of this number here. Now at this point, I'm not doing anything to the x coordinates of my parent. So I'm just going to copy them down. But I am going to impact the y coordinates by a factor of 2. 1 times 2, 1/4 times 2, which is a half, 1/16 times 2, which is an eighth, 4 times 2 is 8, 16 times 2 is 32. And now I'm going to do the translations. That's just another word for shift or move. Tell me the horizontal shift, Jalen, according to this. We're going to shift which way? Left 2. Tell me the vertical shift, Matthew.
Move down 3.
Down 3. All right, so for this table, we're just going to call it, I'm going to say left 2, down 3. And the way I accomplish that using tables, I can go left 2 by subtracting 2 from each of these x's. So let's do that. 0 minus 2, 1 minus 2, 2 minus 2, negative 1 minus 2, negative 2 minus 2. So that takes care of the left 2, and now let's take care of the down 3. I'm going to subtract 3 from each of these y's. 2 minus 3, 1/2 minus 3, 1/8 minus 3, well, negative 2 and 7/8. I forgot what that is in decimal. Anybody have it already? I'll just write negative 2 and 7/8. 8 minus 3, 5, 32 minus 3, 29. So this ends up being my official graphing table. Any questions on how we got there? Vertical stretch, multiplied by y, left, right, up, down. So let's see, we've got to be able to plot 29 on the y-axis. So any suggestions on what we can do our units in? We've got 9 marks to work with. Any suggestions to plot 29? Well, I know it's going to leave us just a little bit short, but I'm going to go ahead and just do 3s. And we'll just go up above. This is 27. We'll just go up above a little bit. Okay, so let's plot negative 2, negative 1. So remember, this is actually going to be 3, negative 3. So I'm going to go down to about right there. Negative 2, negative 1. Negative 1, negative 2.5. That's a little bit lower. Not quite to negative 3. 0, that's a little bit lower. Negative 2 and 7/8. Really, really close to negative 3. Over here, I've got negative 3, negative 5. Well, this, or positive 5. This is positive 6, so it's just below positive 6. And then negative 4, and this is where we're going to go up to 27, and then we're just going to say it's a couple more, a little bit higher. And let's draw it. Okay, I have a new horizontal asymptote. What is it? It looks like negative 1, but remember I've changed my units, so it's a little tricky. John? Yeah, it's actually y equals negative 3. So make sure when you draw your graph that you're always approaching y equals negative 3, but you should not cross it. All right, we're ready for domain range, and we'll be done with this problem. So who wants the domain? Yes? Okay, interval notation, that would look like what? Okay. What about the range? Kennedy, would you like the range? Okay, so negative 3 would be the low side, and then we'll keep going up from there, so positive infinity. Very good. Yep. Yeah, it's a good question. If you want to use the inequality notation that we've already used, that's fine. There will come a time, and I'll kind of give you a heads up, I will say use interval notation, or I will say use inequality notation. So at this point, I just want you to be ready for either. You should know both. But for now, it doesn't really matter which one you pick. Just make sure you know both of them. All right, that finishes off Roman numeral 2a. Do we have any questions on that? Okay. Don't have a lot left. Let's see if we can work our way through this problem. So let's start by getting a table for the parent function. So if I lift the parent out of this, it's y equals 2/5 raised to the x power. All right, so let's just generate a table of values for the parent. Input 0, output 1. Input 1, output 2/5. Input 2, output 4/25. Input -1, that just flips 2/5 and makes it 5/2, or maybe it's more familiar for graphing purposes to say 2.5. For -2, that just flips over 25/4. That's another way of saying 6 1/4, or the decimal form would be 6.25. Now if I went through that too fast and you don't understand how I got those numbers, let me know. Okay, now let's do it's actually two things involved. We're going to reflect over the x-axis, and we're also going to stretch by 3. So it's actually like two things in one. So let's do the times -3 in our next table. Sam, which of the coordinates from the parent table will we multiply by? X or y? We'll multiply by the y, so I'm not going to do anything to x at this point in this step. But I'm going to multiply -3 times each one of these y coordinates. So 1 times -3, 2/5 times -3, -6/5, 4 times 4/25 times -3, -12 25ths. 2.5 times -3, that's -7.5. And 6.25 times -3 is, what is that? Calculator people, help me out. 0.75. Okay, we're almost there. This didn't print real well. That's a 4. So tell me the horizontal move, Chris. Right 4. Tell me the vertical move, Carly. Up 2. Okay, so let's do right 4, up 2 in this table. I will accomplish right 4 by adding 4 to each one of these x's. 0 plus 4, 1 plus 4, 2 plus 4, -1 plus 4, -2 plus 4. And I will accomplish up 2 by adding 2 to each one of these. -3 plus 2. That's like -1 1/5 plus 2. So what is that? -1 1/5, 4/5, or if you are using a calculator, it probably comes out as 0.8. -12 25ths plus 2. Somebody give me that decimal. -12 25ths plus 2. 1 point what? 1.52. Anybody else get that? Well, you should be adding 2. It's -12 25ths plus 2. Got it right? Okay, -7.5 plus 2, -5.5, and this should be -16.75. So we just have to be able to plot -16 3/4, so we can do our y-axis in 2s, and we should be able to make that happen pretty comfortably. So this is the table that we're going to plot. This will represent our graph. All right, so 4 -1, 5 4/5. I'll just estimate, since those are 2's, it's just above the x-axis. 6 1.5. So 1.5 should be pretty even closer to 2. A little bit higher than this one here in the middle. 3, -5.5. So 2, 4. This is -6, so we'll just place -5.5 right in between. And then 2, 4, 6, 8, 10, 12, 14, 16, and then a little bit more. All right, so we have a new horizontal asymptote, and what is it? Yes, Matthew? 2. Y equals 2. So this isn't required, but it's a good reminder for me. K will always tell you what the horizontal asymptote is. So we're approaching, but never touching y equals 2. So there's the rough sketch. All right, questions? You're doing great. Let's try one more problem, and then I'm going to let you have the rest of the time to work on this. I wanted to help you out with one of the word problems. You actually have 3, I think, in this assignment. This one's pretty close to number 26. One thing that you will need to do, I realized after I printed these notes, I left out, when I typed these up, I left out the cost of the SUV. You need to write that in because that's very, very important. We got to know what the initial cost of the SUV was. So just write that in there at the top of that slide. I just told you an SUV depreciates, but I didn't tell you how much you paid for it. So it's kind of hard to get to the answer without that. Okay, well, first of all, we got to understand what depreciate means. Have you ever heard that term? Depreciation. Give me your own words. What do you think depreciation means? Yeah?
It means like goes down in value.
That's a great answer. Something, an asset, something of value that decreases in value over time. And probably our most common real-life example of that is cars. As a matter of fact, there's a rule of thumb that if you buy a brand new car, and somebody that's in the car business would be able to get this more precise, but if you buy a brand new car, the minute that the tires leave the lot and get on the highway and you start home, 5 seconds after you've actually driven the car, it has decreased in value about $500 roughly because it's no longer new. So if you turned it around right after you bought it brand new and you tried to sell it to somebody else, you'd have to take at least $500 off of the purchase price. And we call that decrease in value over time and usage. We call that depreciation. So depreciation is a classic exponential decay model for us, real life math. Okay, so I want to start off a lot like we did with exponential growth. This is kind of our template, if you will. And yesterday, when we talked about exponential growth, we said that B was identified as a growth factor. And the way we get the growth factor for these word problems is we always start with the number 1, and for growth we add whatever the percentage of growth is. Well, this is decay. So you can probably guess what we're going to do when decay happens. Are we going to add? No. What are we going to do? We're going to subtract. So to get what we're calling our decay factor, we're still going to start with the number 1, but we're going to subtract from it whatever our given percent of decrease is. And we'll come back and put all this together in just a second. So this letter B, when it comes to decay, called the decay factor, this is how you will always find it. You start with 1 and subtract whatever the decrease is percentage-wise. A is still called the initial value, just like it was for growth. And what I mean by that is every time you're given one of these problems, you have to start somewhere. Whether it's population count, we counted the population in the year 2000, it was this. How much did it grow from that point forward? Well, that initial count was A. And then we came up with the growth factor, 1 plus whatever the rate of increase is. Well, this is decay, but it's still considered to be an initial value for this letter A. So in this problem, we'll start putting all the pieces together. We're going to start our initial value, the purchase price was $30,000. And what is our decay factor? Good, 0.85. And we're still raising, just like we did with growth, we're raising this to the x. And x will pretty much always represent a period of time. We want to know how much something either grew over time or lost value or shrunk or decayed over time. And so we'll put some sort of time interval in for x. Now what will that be in this case? What is our time unit in this problem? Yes? Years. So now that we've identified that, the number that we put in for x is going to be a number of years since we bought the SUV. We need to label the x-axis as years. The y-axis is going to be the value, the actual dollar amount value of the SUV. So please remember, a graph with no labels is really meaningless. We don't really have a way of interpreting the numbers. So make sure you provide adequate labels for the x and y axis. Okay, we don't need to choose inputs bigger than 20. We definitely don't want to choose anything less than 0. Does that make sense? What was the value of this van -2 years ago? No, that doesn't make any sense. So the lowest number we need as an input is 0, but we already know what that is, right? At year 0, which means no time has passed, how much was the SUV worth? $30,000. So that's our y-intercept. I'm going to do my y-axis in 5,000s. So this would be 30,000. No time has passed. SUV is worth 30,000. Well, let's just chunk these up into increments of 2. What about 2 years? After 2 years, what is this SUV worth? So grab your calculator and use our function, input 2 for x. And Sam, give me the value after 2 years. Is that right? It should be literally 30,000 in parentheses, 0.85, close parentheses, and then to the second. So, is that what you got, 21,000? Did you enter 30,000 or 3,000? 21,000, and read the rest of that, Sam. 675, yeah, we can round to the nearest dollar. So I just need to see who else got that. Make sure you're able to get that. Okay. Well, that's only going to give you, a total of 4 inputs, I guess. That doesn't count. We know that's our y-intercept. So take a few seconds out of your life and do another input. You're just talking about one more. By the time we had this conversation, you would already had it done. So input 4. Jalen, what's the value of the van after 4 years? Yeah, Kennedy, do you have that after 4 years? We'll just round to the nearest dollar. 15,660. Who got it? All right. So let's plot this. We can plot as we go. I'm going to do my years in twos. All right. So here's 2 years. 5, 10, 15, 20, and then just a little bit more. 4 years. 5, 10, 15, and then a little more. The value after 6 years. John, do you have that? And if you haven't already, go ahead and be working on 8 and 10 for everybody else. Okay, who got that? Raise your hand. All right, good. 2, 4, 6, 5, 10, and then a little bit more. 8 years?
8,175.
2, 4, 6, 8. Here's 5,000, and then just a little bit higher. 10 years. What's the value of this after 10 years? Say it one more time. 5,906. Okay. And let's just jump down to 20 years. So just a bit more than 5,000. Can Riley, can you give me 20 years?
1,160.
So here's 20 years and 1,000. All right, so we're going to get really, really close, according to this graph. We're going to, again, be approaching the x-axis. Is there ever going to be a time where we're going to consider it to be zero value? Theoretically, no, but we have this thing in accounting that does allow us to depreciate down to a dollar value, 0. But according to this, our graph, we're going to get really, really close to 0 value, but we're never going to quite get there. Okay, so this would be, actually, if you wanted to stop this graph at 20, it would have been okay. We don't really need to show it going forever and ever, because they just wanted to know for the first 20 years. Okay, any questions? The big thing for me, it's all big, but I want you to understand how to take a word problem and identify, first of all, is it growth or decay, and then how do I come up with the function? That's going to be pretty important going forward. All right, any questions? You are ready to start the assignment.